Hello again. Having spent the last two videos showing you how to put the type arguments in and where they need to go, let's start learning how we can take them out, how we won't have to write them down all of the time. Writing down these type arguments is tedious and repetitive. Thankfully, it's not error prone and that we'll get told when we get it wrong, but it'd be great to not have to do it. Okay, let me show you how. Here's a version of repeat that doesn't list any of the types on its arguments, which is maybe a little surprising, right? If you read carefully in earlier chapters when we were talking about fix and fun and all of that, you'll notice that we say, oh, the type annotation is optional. And it's true, the type annotation is generally optional. Here, however, it is totally optional. We can just leave it out, and Coq will accept this perfectly well. Repeat has the type that we think it does, and so does repeat prime. So Coq used something called type inference to infer, to sort of deduce from context the types of x. X has to be capital T type. X has to be of type big X. That same problem. And count has to be of type nat. Coq was able to figure that out just from how we use it. If you look at it, you can kind of see, well, look, when we matched against count, we gave the cases for nat right here. So that means count really has to be of type nat. It couldn't be anything else. And then later here, okay, well, this cons, we supply big X and little x to cons. And if you remember cons' type, that means little x has to have big X as its type. Okay, we're returning a list of x's, and that also tells us a little bit about what's going on with this big X. And then Coq just figures it out. Neat. Now, all that said, I think it's good to write the type annotations when you know them, unless you feel like it's super obvious or you're feeling lazy or something like that. But it's really ideal. When we ask you to write code wholesale, we'll typically ask you to write it maximally typed. But it's nice to know that you don't have to get it right all of the time for everything. That's half the story. What's the other half of the story? The other half is type argument synthesis. So that was type annotation inference, where Coq infers the types of arguments. Type argument synthesis says, oh, we're gonna infer the value of type arguments that are being passed around. So here's a version, repeat double prime, that looks like the repeat prime we just saw, but we take it one step further. We're not even gonna bother writing down the type arguments. We're just gonna write underscore. Now we've seen underscore before as a pattern, meaning don't care. And it's not, you can't just freely write underscore in a program and say, I don't care. What this underscore is saying is, hey, Coq, there's actually just one thing that can go there. Could you figure it out for me? And for all the time I've spent ragging on Coq's sort of like smartness levels, it's actually really good at guessing. It figures it out really well. If there's just one thing, Coq will typically find it. So here we say, look, this nil blank, I've set up here the return type list X. This has to be X for it to work out. Coq will figure it out. And similarly, well, look, if this is going to be a list X, well, then that's got to be the same X. And then this cons, it's got to be the same X too. So Coq is able to figure it out. Okay, cool. The good news then is, well, this works not just when you're defining a function like repeat to say, hey, Coq, could you figure out what this argument is for me? You can do it when you're writing something like this. You say cons blank, cons blank 1, cons blank 2, cons blank 3, nil blank, and say, look, yeah. Look, these are all nats. Coq, just be cool. You'll figure it out. Now, if there isn't one, Coq will complain. Okay, now the complaint we see here, if you look at this closely, you'll see that you can actually figure out what Coq filled in everything as. It says cons nat 1 nil nat. Okay, that means this got filled in with nat, this one, and this got filled in with this nat. And it's saying, oh, this is type list nat, but it's expected to have type list bool. Oh, Coq must have filled in bool here. So this is actually exactly the same as the example we saw somewhere further up here. Where's the homogena? There we go. This one. Right, it's the same theory as this example we saw above. We're like, okay, Coq figured out those type arguments, and it's true, those are the only ones that could possibly work there, but it turns out they don't work. Okay, that's type argument inference and that's type annotation inference and type argument synthesis. These two things combined will let us sort of not have to do nearly as much work um, when we're writing down polymorphic functions. There's one more trick that I'm going to teach in the next video, and then we'll really be cooking with gas. Then we'll be able to write nice functions that take advantage of polymorphism and minimize the annotation overhead. Okay, coming at you soon.